Now let's take this example of problem number 44 of your textbook. It says a ball falls on an inclined plane of inclination theta from a height h above the point of impact and makes a perfectly elastic collision. So let us see the situation first. Here you find that the plane on which the ball falls, this is the ball which falls. The plane on which it falls, it's an inclined plane. It's an inclined plane. It's an inclined plane. And inclination is given to be theta. And it falls from a height h from the point of impact. This height is h, right? The ball falls from here to this point. Question is, where will it hit the plane again? It's clear that the ball will bounce and hit the plane again. Now we have to find out this distance r. We have to find this distance r from this point to this point. Now, let us first find out with what velocity does the ball hit the ground. The ground itself here is inclined. The ground is inclined. Now let us say the ball hits the ground. Say the ball hits the ground. The ground with velocity u. Then we know from the equation of kinematics, so u equal to under root 2g. We have seen from the kinematics, this is the equation. Now, when the ball hits the ground, mind it, like in earlier problems, the ground was horizontal and the ball hit it at an angle theta. Here, if you just rotate the ground in this direction, the same situation arrives. So this is not a very big problem. You should be able to solve the problem quite easily. Now, a few things that we need to. Let us consider the y-axis in this direction. Let us consider the y-axis in this direction and x-axis along the slope. Y-axis is perpendicular to the slope. In that case, this trajectory of the projectile is a simple projectile trajectory that we have been dealing so far. There should not be any problem. Now, if this angle is theta, then this angle is also theta. And this velocity u works in this direction. Velocity u works in this direction. And this velocity has a component in the perpendicular direction of, since this is theta, so this is also theta. This component is u cos theta, and this horizontal component is u sin theta. Horizontal component is u sin theta. Therefore, when the ball rebounds, let us take this once again. Let us, if we draw this diagram once again, then what we find that this is the inclined angle with an angle theta. And once again for clarity, then the vertical velocity, the rebounding velocity, and since it is a perfectly elastic, vertical velocity will be the same u cos theta. This is u cos theta, and this velocity is u sin theta. And the projectile will move like this. Here, only one thing is very important. What is the direction of G? This is the G. And G as a component perpendicular to the incline, component equal to G cos theta, and this component is G sin theta. In normal projectile, when the slope is horizontal, then there is only vertical gravitational acceleration, G, downward, but there is no horizontal component of G. Here, unfortunately, there is a horizontal component of G also. This is the only difference of this problem than a normal projectile problem, right? So now let us start solving this. Say it x time t to reach the maximum height x time maximum height is equal to t, but in the inclined xy axis. Inclined xy axis. Inclined xy axis. If it takes time t, then we can write final velocity v is equal to 0 is equal to initial velocity in the vertical direction is u cos theta minus the normal equation. Let us write it here. The normal equation is v equal to u minus gt. This is the normal equation. But here there is a special equation. U is u cos theta, and g, the component of g in the normal direction, is g cos theta. G cos theta into t. From here we find t is equal to u by g. So total flight time, equal to 2t. Now we just have to find out what distance it travels in the horizontal direction by this time 2u by g. But let me correct once again, not exactly in the horizontal direction, but in the x direction, which is inclined. right? Say this range is R. Say this range is R, as we say. So, range R along the inclined plane and plane. The range is R along the inclined plane. Then let's not write so, let's write say. Let's write say. Say range is R along the inclined. Then we use the kinematic formula. Kinematic formula we know S equal to Qt plus half AT square. This is the kinematic formula. So remembering this formula, we can write R is equal to U is initial is the velocity along the direction of motion, which now is U sin theta multiplied by T is 2U by G, 2U by G plus half acceleration in the direction of motion is G sin theta, G sin theta multiplied by T square. T total time, so total flight time, let's say capital. Total flight time is 2U by G. So it is 4U square by G square. This is equal to, here we find 2U square by G sin theta, 2 square by G sin theta, plus here also we find this 2 and 4 gets cancelled. We have 2 here. G and G square gets cancelled. We are left with G here. So here also we have 2U square sin theta by G, or 2 square sin theta by G. So what we have here is both are same. So 4U square sin theta by G. 4U square sin theta by G. Now, this is equal to 4 sin theta by G. What is U square? Under root 2GH. So U square is 2GH. 2 since U is equal to under root 2GH. Then we have equal to 8. G and G gets cancelled. This G and G gets cancelled. So we have, sorry, I have done a mistake. Not 2 gets cancelled. I have 8H, 8H. The range is 8H sin theta along the inclined plane. Along the So this is the answer, right? Now, what we shall do, we shall now also take care of your next problem, because next problem is the same problem with the different condition, with the different initial condition. Next problem you find is Next problem says, solve the previous problem if the coefficient of restitution is E. Value of theta, E, and H, etc. given. Right? Now, you can see that if there is a coefficient of restitution E, then the only change in this diagram, let's draw this diagram here once again. The only change in this diagram is the inclination theta and this is the new y-axis, this is the new x-axis, and this is the projectile. The only change here, the Vy, that means the rebounding velocity in the y direction, will be equal. Instead of u cos theta, it will be eu cos theta. Eu, and the horizontal velocity component remains same as u sin theta. And the components of g remain the same. This is g, and normal component is cos theta, and horizontal component is g sin theta. So it is the same problem. Only thing which has changed is the y-axis component velocity is now eu cos theta instead of simple u cos theta. So we now try to solve the problem in the same way. In the same way, what we have done here, we have done, say the takes time to reach the maximum height, then that time is multiplied by 2 to get the total time. Then with this total time, how much horizontal distance it travels. That is all we have done. So here also, we do the same thing. Here also we do the same thing. Here also we do the same thing. Here, we first find out the time to reach the total, time to reach the maximum height. That, let us say time to reach the maximum height is t. In the same fashion each time. Say time to reach the maximum height then we simply apply kinematic equation. Final velocity is 0 is equal to initial velocity is e u theta minus, instead of g, we write g cos theta, g cos theta into time t. From here we get time t is equal to by g, e u by g, e u. We should also compare this. Earlier we got t is equal to u by g. Earlier we got t is equal to u by g. Now we get t is equal to u by g. So we are perfectly in sync with the problem. Right? Now, so total time of flight So, height and capital T is equal to H. Now, once again, from the range formula, we can find out the range. So range R is equal to exactly the same way we found earlier. Range R is equal to initial velocity is u sine theta, u sine theta multiplied by total time 2e by g plus half into acceleration in this direction is g sine theta, g sine theta into time square. Time is 2e, 2e by g square. This is equal to by g sine theta. Thus, here we have half g sine theta multiplied by 4 u square by g square. Now, here, this 2 and 4 gets cancelled. We are left with 2. And this g and g square cancelling, we are left with g. So this is equal to sine theta by g plus 2 square by g sine theta. I just have to solve this equation or simplify this. This is looks like b. This is 2 u square, u square. So we take 2 sine theta by g outside the bracket. We have e plus square. Now, this is equal to, now and second coming, what is u? U we know from the beginning under root 2gh. So u square is sine theta by g into plus, we write since 2gh. That this is equal to, now this g and g gets cancelled. So what we have, 2s are 2, 4. 4 sine theta. We have 4 sine theta, 4h sine theta. So let us write 4h sine theta. Instead of just 4, let us write sine theta plus u square. Now, just for fun, you can check if there is no restitution. Suppose it is a perfectly elastic collision, then E is 1. So E plus E square equal to 2. So this equation becomes 8H sine theta. Remember that it was the same answer 8H sine theta in our last equation when in the last problem when the collision was said to be perfectly elastic. So this is this. Now we put here the values. The values are given that 4 into H is given 5 meter. Sine theta is given 45 degree. So it is sine 45 degree. 4 into 5 into sine 45 degree. And E is given 3 by 4. So 3 by 4 plus 9 by 16. This is equal to 4 of 5 is 20 and sine 45 is 1 by root 2 multiplied by this is 16 into 12 plus 9 is equal to 20 into 12 plus 9 is 21. Calculate this with your calculator, we'll find it is 18.56 meter. 0.56 meter. The answer is 18.56. 18.56 meter along the inclined plane. Along the here it is complete. Right? Then we shall go to the next problem. We shall take up the next problem.